Good afternoon, everyone. Today I am going to present on flow through a circular tube, which is an important topic in transport phenomena, assumption and shell balance. First, we start with assumptions to simplify the analysis. Flow is steady, no change with time. Flow is laminar, smooth layers. Fluid properties are constant. Flow is only in z direction. We consider a small cylindrical shell of radius r, thickness delta r, and length L. We analyze momentum entering, leaving, and acting on this shell. This method is called shell momentum balance, which help derive the equation. Then differential momentum equation. Now we apply momentum balance on the shell. Momentum in minus momentum out plus forces is equal to 0. Taking limit as delta r approaches 0, we get a differential equation. For fully developed flow, velocity does not change along the pipe length. So dVz by dz is equal to 0. Then shear stress distribution. Next, we find how shear stress varies inside the pipe. We define modified pressure. P star is equal to P plus rho into G into Z. The final result shows that shear stress varies linearly with radius. At the center, stress is finite and it increases towards the wall. Then velocity profile. Now we calculate velocity using Newton's law of viscosity. Shear stress is proportional to velocity gradient. After integrating and applying boundary condition, we get velocity profile. The velocity profile is parabolic. Maximum velocity at center, zero velocity at wall, no slip condition. Then flow rate relations. From velocity profile, we derive important flow relations. Average velocity is equal to U max by 2. Flow rate equation Q is equal to pi r power 4 delta P by 8 into mu into L. Flow rate depends strongly on radius to the power of 4. So small increase in radius gives a very large increase in flow. Then equation of change. Now we derive the same result using another method called equation of change. Start from Navier-Stokes equation, apply assumptions, study incompressible, fully developed. All terms become zero, expect radical viscous term. This simplifies to the same governing equation as shell balance. Numerical capillary radius. Now we solve a practical problem. Convert kinematic viscosity to dynamic viscosity. Convert mass flow rate to volumetric flow rate. Use Hagen-Poiseuille equation. The calculated radius is approximately 0.751 mm. This method is useful in experimental measurements. Vertical tube with gravity. Now we consider flow in a vertical tube. Gravity adds on additional force term. Effective pressure gradient becomes pressure minus rho into g. So velocity depends on both pressure and gravity. Then application and key takeaways. Applications: measuring viscosity, capillary design, microfluids, process pipelines. Laminar flow in a circular tube produces a parabolic velocity profile